That's in fact the same characterization. Whereas for NP, we have this, it takes a different turn. There is this verifier characterization, meaning a language is an NP if and only if it has a polynomial time verifier. That means that for all x that is in the language, there should exist a certificate which can be verified, which can be used to verify the membership of x in the language. So the certificate should be polynomial in the length of x, and the verifier should run in time polynomial in the length of x, right? So that's what I've written here. It's a deterministic polynomial time verifier v such that x is an L if and only if there is a certificate y such that the length of y is polynomial in the length of x, and the verifier can verify the membership of x using y, right? So now let us define what is CoNP. Okay, so maybe I'll just push it a bit down. Okay, so what is CoNP? So definition: a language L is in CoNP, or rather, maybe I'll just write a different way. CoNP is the set of all languages A such that A complement is in NP. Okay, so it is a set of all languages such that A complement is in NP. Okay, if you have a language A that is in NP, then or if you have a language A whose complement is in NP, then A is in CoNP. So CoNP is a class of all languages that are whose complement is in NP, right? So again, just one thing I want to say here. So caution: CoNP is not the complement of NP. It is not the set of all languages that is not there in NP. Okay, it is a set of all languages whose complement language is in NP. Right? It is not the complement of NP. So please, one may be tempted to think that it is a complement of NP. It is not, right? So some examples are SAT complement. So SAT is an NP. The complement language of SAT is SAT complement. Set of all Boolean formula that are not satisfiable, right? Set of all pairs G, K such that G does not have a K clique. So that's a complement of clique, right? These are examples of CoNP languages. These are in CoNP. Another example, okay, so this maybe it will take some time to figure out, or it will take some time to sink in, that tautology. Okay, so what is tautology? Tautology is a question where I give you a Boolean formula and ask Boolean formula phi such that is it always true regardless of what assignment you give to the individual variables in it. So this is unlike SAT, where you're asking is there some assignment such that it will evaluate it true. Now you're asking is this Boolean formula, no matter what you assign to it, is it always true, right? So this is an example of a language in CoNP. Why is it in CoNP? So you're asking whether phi is always true, right? So in other words, you're asking so what are the languages, so what is the complement of this tautology, right? So again, this I am saying that tautology is in CoNP, right? I am saying that this is in CoNP. So what is the complement language of this? This is the complement language of this is the set of all Boolean formula such that it will not be always true. it will evaluate to false in some assignments, right? So if phi is not in tautology, that means it evaluates to false in some instances. So now if you take the complement of phi, right? So this is what I've outlined here as an exercise. If you take the complement of phi, then the complement of phi will have some assignment that evaluates to true, right? So phi is not in tautology means there is some assignment which will make phi evaluate to false, right? Because otherwise it will be in tautology, right? And that means that the complement of phi, right? So the complement means it's just flipping the evaluation. So phi does not always evaluate to true, and phi complement does not always evaluate to false, which means phi complement sometimes evaluates to true. In other words, it means that phi complement is satisfiable. So checking whether if phi is in tautology, the complement of phi is, or if a language phi is in tautology, whatever is not in tautology, its complement is insatisfiable. It's insatisfiability, right? So that is why tautology is a CoNP language, right? You are asking whether it always evaluates to true, regardless of what you assign to the variables. Another way to look at it, right, is this, right? So let's say L1 is in CoNP, right? We had this characterization. So you have this many different computation paths. A language is in NP if now how do we check if X is in L1 or some string is in L1? It should have some accepting computation paths. So there's one and there's another one, right? So there are accepting it has to have some accepting computation, right? Whereas if a language is in CoNP, then we want all the paths to be accepting, as is written here. All the paths should be accepting. None of the paths should be rejecting, right? So you can see why now why a language is in CoNP and its complement will be in NP, because if you take the complement, then all this will be reject, right? All the accepts, sorry, if you take complement, it will not be all accepts, which means it will have at least one reject. And if you take the complement of that language, that means that it has to have at least one accept, right? So what I'm saying is that L2 is in CoNP. The complement of L2 means that it cannot be all accept. If you put it on the same machine, it cannot be all accept. There has to have at least one reject. But that's the same as if you relabel reject and accept. It's the same as asking there has to be at least one accept, which is what we check in NP. Okay. So that is another way to kind of understand CoNP. And just like we had this kind of descriptions over here, the verifier based description, we have also a verifier based description for CoNP. So I'll write it here. L is in CoNP if there is a deterministic polynomial time machine V such that X is in L. Okay, the complement of X, L is in NP, right? So this entire thing over here, that there X is Y, etc., this entire thing will be flipped. So for all Y such that length of Y is polynomial in the length of X, Vxy will be 1. Right? So what is happening here is that here we want for all the Y's, we have to, the verifier should evaluate to 1. So which is the same as saying here for all the paths we want it to be accept. Whereas in NP, we just wanted one accepting path, right? Which is like the quantifier here in LP. In NP, we say there exists quantifier. It's an existential quantifier. Whereas in CoNP, we want a universal quantifier. So there is an inherent kind of difference, right? So here we want all the paths to be accept, whereas in NP we wanted only one accepting computation, right? Okay, now some points, CoNP completeness. So just like NP completeness, we could define CoNP completeness. So a language A is CoNP complete. So this is exactly like NP completeness. If one, A is in NP, and two, for all B is in sorry, I'm sorry, it's not exactly like NP completeness in the sense that it is not always, we don't want A to be in NP, it is analogous. So we want A to be in CoNP. For all B in CoNP, we want B to be reducible to A. So this is exactly like NP completeness, except that A should be a member of CoNP instead of A being a member of NP, and B should be all B in CoNP should be reducible to A instead of all B from NP to be reducible to A, right? Some minor points, and I will stop this small lecture with that. So these are things that you could work out. I'll just give you high level ideas. So one is that A is CoNP complete if and only if its complement is an NP complete, right? So SAT complement, for instance, is CoNP complete because the complement of SAT complement is SAT, which is NP complete, right? Why is this true? So what are the analogous requirements for NP completeness? The complement should be in NP, which is true by the definition of. So I'm just writing the NP complete definitions. A should be in NP. This is the NP complete definitions. And two, for all B in NP, B should be reducible to A, right? These are the two requirements. So one, that A is in CoNP is satisfied by definition of CoNP. Then all the B that is in CoNP reduced to A. So we already have A complement is NP complete. So which means maybe I'll modify A complement is an NP and all B in NP reduces to, or let me use a different symbol, C in NP reduced to A complement. Now this means that consider all B in NP, right? B in CoNP. Now B complement is in NP, right? So B complement reduces to A complement, but the same reduction, if B complement reduces to A complement, that means B reduces to A, right? Because no maps to no, yes maps to yes. So you can work out the details. That's how this is done. Sorry. Second, P is contained in NP and CoNP. Why is this true? Well, we already know that P is contained in NP. Why is P contained in CoNP? Pretty much the same reason, right? So if you don't have any non-determinism, if you have a deterministic polynomial time machine, it is where there is no non-determinism, all the computation paths lead to accept. So you can think of a deterministic machine itself as a CoNP machine, deterministic polynomial time machine itself as a CoNP machine, right? So you have just to make a distinction, you have just this kind of thing, right? So this, if the language is in, if the string is in the language, then this is accept. If the string is not in the language, this is a reject. So if it is an accept, it satisfies this as well as this, the condition for NP as well as the condition for CoNP, right? So any language in NP is also in CoNP. Sorry, any language in P is also in CoNP. So again, you can write down the details of this. And another way to see it is that if slightly long-winded way to see it is, if A is in P, then A is in NP. Sorry, a complement is also in P, right? If a language is polynomial time, then the complement is also in polynomial time, right? It's just flip the output. This means that a complement is in NP, right? Because P is contained in NP, which means that A is in CoNP. Right? This is another way to see the same thing. Again, in fact, I have written down the answer for you. Finally, if NP and CoNP are distinct, show that P and NP are distinct. Okay, so this seems like a tricky question, but it is easy once you see it in the contrapositive. So this is what we want to show. Instead, what we will show is, we will show P equal to NP implies NP equal to CoNP. So if, okay, this is what, and this I think is easier to show, right? So you can think about this. So because if P is in NP, P is equal to NP, that means all the languages in NP are also in P. If you take a complement of a language in NP, so all the, what is CoNP? CoNP is a class of languages that are the complements of the languages in NP. But then NP is equal to P. And P is a class which contains its own complement. Right? If a language is in P, and if you take its complement, then the complement also will be in P. So, for instance, if to check whether a graph is connected, it's in polynomial time. To check whether a graph is not connected is also in polynomial time, because you could just take the same algorithm and just make accept into reject and reject into accept. Right? So P is a class which contains the complements. NP is not such a class, or at least not as of now. But if P equal to NP, then NP will also be such a class, which means that CoNP will also coincide with the complement. So P equal to NP means NP and CoNP will also collapse to P. Hence, if P equal to NP, NP is equal to CoNP. So this implication is true, which means the contrapositive should also be true, which is what is given in the statement. Right? So we defined CoNP, which is the class of all languages whose, once again, it is not the complement of the class NP itself. It is a class of all languages whose complement are in NP. Right? We saw the verifier based characterization. So we want X is in a language L which is in CoNP. If for all the certificates that you take, the verifier should be able to verify that X is in the language using all the certificates. Like all certificates lead to accept. In the computation tree form, it is like this: all the computation paths lead to accept. So the example of any language in NP whose complement, so SAT complement, click complement, and another language is tautology. So tautology is kind of like SAT complement, right? Just by flipping the yes and no. Then we defined CoNP completeness and saw some examples. With that, I will stop this small lecture. Thank you.
Swayam Prabha, Digital India, Educated India.
Welcome to this lecture. In the last lecture, we had just started to discuss about the bridge pattern. The bridge pattern is an extremely useful pattern, helps to simplify the design, makes it more maintainable, extendable, very popular pattern. Let's look at this pattern. If you remember, we were discussing towards the end of the last lecture the structure of this pattern with the help of some examples. Let's just recollect the structure of the bridge pattern that we were discussing last time. We had taken the example of a shape, various types of shapes, geometric shapes, line, triangle, circle and so on. And then these are to be drawn on various platforms, on the desktops, mobile phones and so on. And then we had discussed about the class hierarchy that kept on becoming more and more complex as we used a different application like animation, or we used a different platform. And the solution to that, we had drawn the bridge pattern. Here on the left side of the pattern, we have the abstraction hierarchy. These are the general concepts which typically don't change too much. On the right side, there is another hierarchy, which is the implementation hierarchy. And here it's more likely to change as new platforms become available, new applications become available and so on. And we had said that the number of classes here, if we use bridged pattern, is quite manageable, understandable. But if we don't use the bridge pattern, just use a class hierarchy as it is, then the number of classes grows very rapidly.